So, redox reaction stands for oxidation reduction, but redox for short. Remember, we are transferring electrons in a redox reaction. So they're not sharing, they're transferring outright their electrons. All single replacement, combustion, many synthesis, and decompositions are redox reactions. Okay, many redox are more complex, and we can't just balance them by looking at them. So I don't know if you remember the half reaction where we break it up into what's being oxidized, what's being reduced, and then we balance it and put it back together. So that's what we're going to refresh our sweet little minds with. Okay, terms to know, there we go. Oil rig stands for oxidation is loss, reduction is gain. We're talking about the electrons. So the species that is losing the electrons is oxidized, and its charge will increase. Okay, and the reason its charge increases because it's losing electrons, which are negative. Okay, so its charge gets more positive. And the reduction is they're gaining electrons, so their charge will decrease or be reduced. Okay, because they're gaining things that are negative, so they will get less positive or more negative. And then the oxidation number, remember, is that arbitrary number that we assigned so that we know what's going on with the electrons. And there's some rules about how to assign those. Okay. So we'll start with that. Sometimes it's called oxidation state, sometimes oxidation number. Okay, I usually say oxidation state. I might say number. If it's an element, a free element, it's 0. So any free element has an oxidation state of 0. Okay. If it's a monoatomic element, mono meaning 1, and it's become an ion, say like sodium. Its oxidation number or state is going to be what its normal charge is. So everything in group 1 is going to have an oxidation state of a +1, just like its ionic charge. Okay, everything in group 2 would have an oxidation state of +2. Okay, so if it's monoatomic. If not all of them, there are some that can change, especially when we get over there to the halogens. Chlorine and bromine can be all kinds of things. Nitrogen can be all kinds of things. Okay, but if it's monoatomic, like one element with another thing, then it's going to have its charge. Okay, oxygen is normally a -2 unless it's in a peroxide, and the way you know it's a peroxide is if it looks like it shouldn't go together. For instance, Na2O2 is a peroxide, and so then the oxygen would be a -1. Okay, hydrogen normally a +1, although in hydrides, metal hydrides, it can be a -1. So I think that was something that got somebody on those nomenclatures quiz. It was like lithium hydride, LiH, and it's hydride in that case. Fluorine is always a -1, will never be anything else. And then here's what gets people, if it is a compound, the oxidation sum, they have to add up to 0. Okay, if it is a ion, it adds up to the charge of the ion. Okay, so if I had sulfate, which is a -2 charge, the oxidation states of the sulfur and the oxygen in there are going to add up to a -2, not neutral. Okay? So there are the rules. Let's practice assigning them. So in these compounds, let's assign them for carbon and oxygen. Okay? It didn't say anything about carbons, but it does say that oxygen's a -2, right? So we know that oxygen's is a -2. So I put it above it. You can put it wherever you want. I usually just put it above. Okay, but the fact down here that I have 2 means I have a total of a -4 charge total. So what does that make carbon have to be? +4. So carbon's going to be a +4. I don't care if you put the plus sign before or after the number. Technically there is a correct way, but I don't care. So just do it. You can do 4 plus or +4. I don't care. Okay, as long as you know it's positive or negative. Okay, so in SF6, what do we say fluorine is? -1. Okay, so that means I have a total down here of a -6 because there are 6 fluorines. So what does my sulfur have to be? +6. And then nitrate has an overall charge of a -1. So I know that oxygen's a -2, but I have a total of -6. So what plus a -6 will equal a -1 plus 5. So do you remember how to do that? Do I need to do some more examples? Because I can make up some stuff. We're good? Okay, so that's how we assign oxidation states. Actually, that was on the AP exam last year. They had one that they had to assign the oxidation state, and as far as I know, everybody got it right in my class. At least the ones that came back and, you know, even though they're not supposed to tell me that. Okay, so what we're going to do here is we're going to assign oxidation numbers to everything, and then we're going to determine what is oxidized, what is reduced. Do you need to go get some water? You okay? Okay, so exercise 17 gives us this reaction, and right off the bat I see that I have two free elements, so what are their oxidation states? 0. So we're going to go ahead and assign those, and then what is iodine going to be? It's group 17, it's monoatomic here. It's going to be a -1, but there are 3 of them, so what is aluminum going to be? +3. Okay, so aluminum's going from a 0 to a +3, so what did it do? Did it gain or lose? It lost 3 electrons, right? So aluminum is oxidized. Okay? Iodine's going from a 0 to a -1, so it gained 1 electron. So iodine is reduced. Apparently I don't know how to spell reduced. Okay? So far so good? All right, let's do some more.
How many electrons did it gain?
It gained 1,
Just one.
but if you notice, was that balanced? I didn't even notice. Each individual iodine gained 1, but you have to balance that with 3, so a total was going to be, actually the total should be 3.
It gained 3.
Each iodine gained 1,
Oh, okay.
but when you do, yeah, when we balance them, they have to match each other.
Okay.
But individually, the iodine gained 1, and the aluminum lost 3. Okay. All right. So let's do this one real quickly, because the hard part, not the hard part, but the more difficult part is balancing them, not deciding what's oxidized and reduced. That's pretty easy. So I have lead 2 sulfide plus oxygen going to lead 2 oxide plus sulfur dioxide. So first thing I do is as soon as I see a free element, I know it did something. So it's a free element here, so it's going from a 0 here to a -2 over here and a -2 here. So oxygen gained 2 electrons, right? So I know that O2 is reduced. So now I need to look at lead and I need to look at sulfur. So if I look at lead, it stayed +2 on both sides, yes? Do you agree with me? So +2 and a +2. So lead didn't do anything, okay? So right away I know that sulfur had to be the one that oxidized, because remember, you can't have a reduction without an oxidation or an oxidation without a reduction. And they happen simultaneously. They do not happen one thing's oxidized and the other thing's reduced. They happen at the same time, okay? So sulfur is going from a -2 here to what over here? That doesn't look like a negative. Let me make sure you see that's negative. So what is sulfur over here? +4. So it definitely lost some electrons. So the sulfur is oxidized. Okay? And the next one, also right away, I see that I have lead as a free element on one side, not on the other, so I know lead's doing something. So over here, it's a +2. Over here, it's a 0 because it's elemental. So lead did what? Did it gain or lose? It's going from a +2 to a 0.
Lost. No, gained.
Gained. Lead gained 2 electrons, right? So it is reduced. And then let's look at carbon, because I have CO going to CO2. Oxygen is a -2 in both of those cases. So oxygen's a -2. So this one is a +2, and this one is a +4. So it definitely lost 2 electrons, right? So it was oxidized. So now that we know how to recognize what is oxidized and reduced, we are ready to balance redox. Love to balance redox reactions. They're fun, fun, fun. Okay, here is the method. I'll walk you through it very quickly, and then we'll just work some. Okay. First of all, we're going to write the skeleton half reactions, meaning break them apart into their oxidation and their reduction. We break them apart. Then we're going to balance all of the elements other than oxygen and hydrogen. We save those for last. Okay. The only way that we can balance oxygen is by adding water to the other side. If I add water, what does that do to my hydrogen? Knocks it out of whack. So then I have to add, not necessarily double it, because you may already have some hydrogen on the side, so don't think double it. You're going to have to add however many hydrogen you need to now balance that out. Okay. Then we have to balance the charge. We don't normally do that in normal reactions, but we're going to balance the charge by adding electrons to one side. Okay. If you are balancing your half reactions and you added electrons to the same side of both of the reactions, you did something wrong. One of them should have electrons on the product side, one of them should have it on the reactant side. If I am oxidized, where should my electrons appear? As a product or a reactant? If it's an oxidation, where should your electrons appear? Product or reactant? Product, because it's losing them, right? They're going away. So if it's a reduction, the electrons should appear on the reactant side because I have to add them to that because they're gaining them. Okay? Then you add the half reactions back together, canceling out what appears on both sides, and then bam, you got a balanced reaction. Unless it's basic. Okay? If it's basic, that last step is however many free hydrogen you have, you add that many hydroxide to both sides. The hydroxide and the hydrogen make water, and then you might have to do some further canceling out. So we're going to do an acidic one first, okay? And then we'll do a basic one. All right. These usually take up quite a bit of space, so either write small or I have paper. So I have this sample problem that we're going to balance as a half reaction in acidic. Acidic is always better because we don't have to do that extra step. If it doesn't tell you acidic or basic, assume that it's acidic or neutral. And then you do neutral the same way. Don't do the basic thing unless they say in a basic solution, because that's an extra step. Okay? So we're going to break these into our half reactions. Clearly, these go together and these go together. So we're going to do the easy one first, right? So we're going to do Fe2 plus going to Fe3 plus. So my iron is already balanced, so the only thing I need to balance here is my charge. And how would I do that? I'm going to add one electron over here, right? Because I need both sides to be a +2. Okay? Because the only thing I can add to balance charges are electrons. Okay? So I have to add an electron to the product side because I need that to be a +2. Okay? Now let's go with... We'll make it look like Christmas. Let's go with red. So now I'm going to do Mn, and that's supposed to be O4 like this. It is a typo. And it's going to manganese 2 plus. So my manganese is already balanced, so I can leave that alone. And so I need to balance my oxygen. So the only way I can do that is to add 4 water to the product side. And now I need to add some hydrogen to the other side. So I'm going to add 8 hydrogen over here. And now I need to balance my charge. Okay. On the product side, I currently have a +2 charge. And what's my charge on the reactant side right now? 7 plus. So how many electrons do I need to add to my reactants? 5. Okay. So now I have both half reactions balanced. Now I need to look at them, and I need the same amount of electrons being exchanged. Okay? So right now I've got 5 and 1. So the easiest thing for me to do is multiply the top by 5 so that 5 electrons total can be lost by the iron so that the 5 can be gained by the manganese. So I would rewrite this down here as 5 Fe2 plus yields 5 Fe3 plus 5 electrons. And now I'm going to add them back together crossing out what appears the same on both sides. On this one, it's only the electrons. So crossing out, crossing out. And then I rewrite the whole thing. So 8 hydrogen, MnO4 minus, plus 5 iron, 2 pluses, yields Mn2 plus, plus 5 Fe3 plus, plus, not 5, 4, sorry, plus 4 water. And that would be my final balanced redox reaction for that particular reaction. Okay? That one was a fairly straightforward, easy one because when you keep the iron with just nothing exchanging, it's easier. Okay? Later on, you may have water on both sides or whatnot. We'll do another one.
Miss Margaret, you always cross out the added electrons? Is that always-
Yes, because they're on opposite sides. So it doesn't mean they're not being exchanged. They are, but they're not going to appear in the overall balance equation. So yes, if you're doing it correctly, you should always be able to
Eliminate.
cross out your electrons, because that's also showing you that one was oxidized, one was reduced. That's why I said earlier, if you find yourself putting electrons on both of the half reactions on the same side of the equation, you did something wrong. Yeah. And that's sometimes a pretty big clue is when you balance something wrong in there, because you're putting, like if you're putting electrons on both of the product sides, then something has run amok. Okay? All right. I said exercise 19, work on your own, but I think that's because I wanted to come do a basic one. But I mean, we can do that one if you want. We have time. Tomorrow I'll let you work on redox tomorrow, so I'll do this one if you want. Okay. Hopefully I don't make a mistake, because I haven't worked it out myself. Okay. So in this one, we're going to have, let me say that I want to write. We know that the dichromate, Cr2O72 minus, is going to the Cr3 plus. And I'm going to do something crazy here right now. I'm going to leave out the H2O and the H plus, because I'm going to come up with those on my own. So I'm going to do the other half reaction is the alcohol, C2H5OH, going to, for now, CO2. I promise you we'll pick up the H2O and the hydrogen in a minute. And does this say if it's acidic, or does it not say? Okay, so it's either neutral or acidic, so we don't have to do the whole OH thing. Okay? So let's go ahead and do this one first, this half reaction. So Cr2O7, 2 minus, yields Cr3 plus. So what's the first thing I need to do? It is not add water. The first thing I need to do is put a 2 right here, because that will trip you up later, and that's usually what the pre-AP kids do wrong, is they forget, I got to balance the chromium, because that changes my charge, right? That definitely affects your charge. So now I want to fix the oxygen problem. So I'm going to say plus 7 water, right? And now how many, 14? Plus 14 hydrogen. I'm running out of room. Okay? So now let's balance our charges. Okay? And see if we do this right. I have a plus 6 on the product side. What do I have currently on the reactant side? Plus 12. So how many electrons do I want to add over there? Plus 6 electrons. And I did not leave myself enough room here. Hopefully y'all can read what I'm writing. Okay? So now we'll do the other half reaction. So we're going to do C2H5, which is ethanol, going to CO2. So what do I need to balance first? Probably the carbon, yeah. Okay, so now I have 2 carbon on both sides, so I'm good to go there on the carbon. Yes?
Why is it 6 electrons and not 9 1?
Because I'm trying to get to a plus 6, because this side is plus 6,
Oh.
and I need this side to be a plus 6, and I had, without them, I had a plus 12. So if I had 6 electrons, now both sides are plus 6. Okay? All right, so now I've got the carbon balance, so now what do I need to do with oxygen? How many water do I need to add, and where do I need to add it?
3 on the left. 3 on the left. Reactants.
I feel some disagreement going
Wait, I
on.
don't just one.
I have 4 oxygen over here. I have 1.
3.
So I need to add 3 water to the reactant side. So 3H2O. Right? Now I got how many hydrogen? 12 hydrogen. Good job on spotting the hydrogen on the end of the alcohol. So that means I need to add 12 hydrogen over here. Well, looky there. I have no charge on the reactant side at all, and I have a plus 12 on the other side. So I need 12 electrons. Okay? So that does not balance out with the first half reaction. I only have 6. So what do I need to do to the first half reaction? Multiply by 2. See, y'all remember this. So multiply by 2. So now we're going to rewrite everything to make it easier to add together. So I have 12 electrons plus, dang, that's a lot of hydrogen. 28 hydrogen plus 2 dichromates yields 4 chromium 3 plus 14 water. Now we're going to add those two together, and we're going to cross out what appears on the same side, on opposite sides. So right away I know I can always get rid of my electrons. So let's do that first. Crossing out, crossing out. Okay? So I got a whole lot of hydrogens. Here I have 12. Here I have 28. So I'm going to cross that out. And how many will that leave me? So what I do, this you don't have to do it this way. It's just something I do is I cross out and I do 16 and I circle it, and that's just so I know that I already crossed those out. You can do whatever method you want. It's just what I've done to keep track of things over the years. Okay? And then I have waters going on too. Okay? So I'm going to get rid of these 3 and I'm going to make this one be 11. So now I will rewrite everything, and then I'm going to double check that everything's balanced and that my charges are in check. Okay, so here we go. We have C2H5OH plus 16 hydrogen. Again, it does not matter what order you're doing these in. Whatever you see first, do first. Yields 2 CO2 plus 4 chromium and 11 water. Forgot the 11. All right, let's double check. Does everything balance? Do I have 16 hydrogen on both sides? Not 16 hydrogen. Wrong. 16 plus 6. Do I have 22 hydrogen on both sides? Sorry about that. Yes. Do I have 4 chromiums on both sides? Yes. Do I have 2 carbons? Yes. 14, 15. Do I have 15 oxygen? Yes. So, and my charges are balanced, so we're good. Do you have a question?
Yeah, so why didn't the hydrogen in the H2O in the original equation matter at all?
We took care of it later.
Okay.
If you put it in with the original equation, it complicates things greatly.
Okay.
So when you see like that, when you see hydrogen and water, leave it alone because we'll take care of it when we're balancing it.
Okay.
It makes life easier. You could have done it the other way, but it just makes it a little bit harder to keep up with. So just leave them out. That's the only thing you'll leave out. Okay? It's the only thing you'll leave out when you're doing the half reaction. So let's do a basic one, okay? Does everybody have this before because once I go, it goes. All right, basic solution. Oh, it's a pretty easy one. Maybe not. Okay, so clearly the Ag goes with the AgCN2 minus and the AgCN also, okay? So that's our first half reaction. So we're going to have Ag plus Cn minus. Does anybody remember what ion that's called? Cyanide. Yep. Goes to AgCN2 minus. So let's fix that one real quick while we're there because it's easy. I need to put a 2 here, right? And then what does that do to my charge? I'm only doing the Ag and the Cn half reaction. So where and how many electrons do I need to add to this equation?
One on the reactant.
1 on the reactant side. Really? I got a 2 minus and a 1 minus.
Oh.
Oh, on the product.
1 to the product side, so 1 electron. It's okay. So my next half reaction just has O2 going to nothing.
How does that?
How does that work? It works like this. O2 goes to, how do I balance oxygen? To water. And then now good job. That's a starburst, I think. Hope you like pink. Everybody else should watch out as I throw.
Oh.
Okay, so I have 4 hydrogen that I need to add to this side. Yes?
Yes.
Okay, now how many electrons do I need to add? 4. Y'all are experts already. So what do I need to do to the first reaction? Multiply by 4. Normally I would just make everything a 4, but I don't want to confuse y'all, so I'm going to multiply by 4 and rewrite it. So 4 Ag plus 8 Cn minus yields 4 Ag 2 plus 4 electrons. Now we're going to cross out what appears the same on both sides, which is pretty much the electrons, yeah? No, yes. Electrons, electrons. So now I'm going to rewrite it. So I have 4 hydrogen plus O2 plus 4 Ag plus 8 Cn minus yields 2 H2O. Now, if this were neutral or acidic, we'd be done. But alas, it is not. So the next step, whenever you have a basic solution, is however many free hydrogen you have, you're going to add that many hydroxide to both sides. So I have 4 free hydrogen, right? So I'm going to add 4 hydroxides here and 4 hydroxides here. Guess what these like to make? Water. So they make 4 H2O. Well, now I have water on both sides. 4 here, 4 over there. So what am I going to do with the 2 waters on the product side? I'm going to make them go bye-bye, and then I'm going to change this one to 2 because they cancel each other out. So now rewrite the final thing. So 2 water plus O2 plus 4 Ag plus 8 Cn minus yields 4 Ag Cn 2 minus plus 4 hydroxide. And that is your final. Sorry, it's not very legible down there. Any questions? We are not doing another one. There's not another example. I do want to talk a little bit about oxidation reduction titrations, and then we're done for today. Okay? So, no, we still have spectroscopy to go. Okay? So, oxidation reduction titrations, the format of a titration for oxidation reduction reaction works the same in terms of burette and all that stuff. But those you almost exclusively have to have an indicator because we're not dealing with pH there. So we're going to have some sort of indicator that changes colors based on whether it's got an acidic proton or whatnot. But this is the most common oxidizing agents. Okay, the AP no longer requires that you learn those terms, oxidizing agents and reducing agents. But basically, it's the opposite. If it causes, so the potassium permanganate is a very common oxidizing agent. It actually itself is reduced, but it causes what it's reacting with to be oxidized. That's why I call it an oxidizing agent. But they don't use those terms on the AP exam anymore. They used to. I made you learn them in pre-AP, but it's not tested on the AP exam. But basically, you titrate it and whatever is oxidized or whatever. Make this correction in your note. It says in calculations, work like them like acid-base titrations, but that's not true. You're going to use stoichiometry for these. That formula MAVANA does not work for redox titrations. And the permanganate, when you titrate with it, it's really pretty because it's like a dark, dark purple, and it changes color. It's really pretty. Okay, but basically, it's dark purple when it's in the permanganate form, and then when it goes to the Mn2+, it becomes colorless. So that's how you know you reached your endpoint, when it becomes colorless. Okay, but it's the titration itself, the technique of titrant and analyte and all that stuff, burette, all that stuff is still the same. It's just now with acid base. Instead of acid base, we have it with a redox. Okay, and that is where we stop today.